thanks a lot to the organizers for being able to get this, for letting me give this talk. This is going to be about pseudo-Riemannian manifolds. So not just Lorentzian manifolds, but any index or any signature. And what we want to consider is some pseudo-Riemannian manifolds have when they carry a large isometry group. So first I'm going to describe kind of the basic object, simple Lie groups. The basic idea here is to follow Zimmer's program, Gromov-Zimmer machinery, and at the end, some results that come out of these considerations. So first part is really just establishing some notation. Some of you might already know it very well. So you take a Lie group with a Lie algebra H, and of course we have the conjugation, which is a diffeomorphism. If you take the derivative, the adjoint representation. And you take the derivative again, you get the adjoint representation, but now of the Lie algebra, and that actually gives you the Lie brackets of the Lie algebra. This is very algebraic, very simple, and out of that, you get a nice object called, it's a symmetric bilinear form of the Lie algebra. Just the bilinear form associated to the adjoint representation. The traits are simple. If H, Lie algebra, has no ideals and the dimension is bigger than 1. Nothing normal within the Lie algebra or the Lie group, and you just want, that's the only restriction here. About simple, this way, pseudo-Riemannian geometry, and H is a simple Lie group. The key of its Lie algebra is non-degenerate. So you have the means to consider some symmetric bilinear non-degenerate form. The Killing form turns out to be invariant by the adjoint representation. This is more or less clear because all the constructed. It's invariant under the adjoint representation. Because of that, it's basically invariant under conjugation. So you can take this Killing form, which is split over your group, either by the left or the exact same result. And that's how you get an invariant pseudo-Riemannian metric, any simple Lie group. So here is the statement, which is, as I said, basically a connected simple Lie group. Then there is a left and right, that's bi-invariant, H bi-invariant pseudo-Riemannian metric group, whose value at the end is just the Killing form. Say about this metric, the index is unique in what you take any other bi-invariant pseudo-Riemannian metric, the index is going to be exactly the same. Actually, up to a constant factor, at least when the complexification is simple, that's the only, there is really another choice if complexification is simple. And you know very well the group of this object. Left and right translations, that's the connected component of the group of isometries. So really very simple. What about the index, the behavior of this to have actual pseudo-Riemannian manifolds? If H is a compact simple Lie group, then the bi-invariant metric is really Riemannian. Those are the non-compact simple Lie groups. You have a bi-invariant metric which is Riemannian. These are class Lies that you consider both over the real simple, for example, SO4 or SO22, but basically you have everything that is simple. So you have any pseudo-Riemannian manifolds with large groups with X. Now this is about Lorentzian geometry, of course, and I can say that only simple Lie group that carries matrix. All of the other groups are either Riemannian or one. Now, construction a step further. So I'm going to take what is called a lattice. That's a non-compact simple Lie group in H. A lattice on a non-compact simple Lie group is a discrete subgroup so that the quotient has finite volume. The volume I'm using here is just the pseudo-Riemannian invariant Riemannian structures. Every simple group has lattices, both co-compact and out of that you can build a new pseudo-Riemannian manifold, which is actually nice, this H mod. So you take a non-compact simple Lie group, consider some lattice, because the H is invariant, gamma still has the left side to admit a left. So with this construction, H mod gamma is finite volume, in some cases compact, and has a large isometry group given by H itself. That's the basic model we want. It's an example of the Riemannian manifold with many isometries, with a large isometry group, and maybe more importantly, complicated dynamics. The thing is that this is finite volume. As I said, in many cases it is compact. Yes, I got some message. In the sense that H mod gamma has finite volume, but still there is a non-compact group acting isometrically on this finite volume manifold. So the effect of that is that many of the orbits have to wind around the manifold in a complicated way. Some problems to consider provide more examples of this kind of pseudo-Riemannian manifolds, determine the structure of finite volume manifolds with this kind of behavior, with a large isometry. And this is where Gromov-Zimmer machinery enters. After all, well, these two problems can be considered in many different situations. I'm going to consider them in the context of Zimmer's program. So here is what is stated as Zimmer's program. This is really kind of a conjecture. The conjecture is the following. If you have a non-compact simple Lie group, try to study the structure of G actions with complicated dynamics of finite volume manifolds. That's the, you can say, the program part. The conjecture part is that somehow you will be able to prove that every such manifold can be obtained from some other non-compact simple Lie group and a lattice. So the claim, the conjecture is that there are not many examples of finite volume manifolds that admit non-compact simple Lie group actions. We have to come always from the kind of construction I considered before. Now, complicated dynamics might mean several things. What I'm going to consider is ergodic actions. So null and connected sets are the only invariant measurable sets, or non-transitive actions with dense orbits that have some dense orbits. And from now on, G will denote a non-compact simple Lie group acting isometrically on a finite volume pseudo-Riemannian manifold. Because we want complicated dynamics, we will assume there are some dense orbits. A number of properties have improved over the years. Some interesting kind of basic properties can be obtained just from this hypothesis. A very important one is that the action of G on M is automatically locally free. The stabilizers are discrete. This is very non-trivial because in particular, it tells you that somehow are immersed within your manifold, and the orbits are quotients of the group G itself by some discrete subgroup of G. So how the group is living inside of your manifold, In particular, the dimension of the manifold has to be bigger than the dimension of the group. Of course, once you have local freeness, you have a foliation by the G orbits. And this is telling you something about the manifold. It has to have a foliation that involves the whole group. Some notation here. If you take an element in your Lie algebra, X star is the induced vector field on your manifold. Just exponentiate, let it act, and then take differential. This implies that these vector fields never vanish. These vector fields are actually the spanning fields for the tangent bundle to the foliation O. Another property which follows from the theory of rigid geometric structures due to Gromov is somehow it's saying that besides the action of G, there are lots of extra isometries. For a dense subset, every point in this dense subset, there is a representation, a homomorphism, non-trivial, from the Lie algebra of your group into the local killing fields, the Lie algebra of local killing fields that satisfy these properties. All these fields, rho x of x, vanish at the point. In particular, they cannot be the vector fields given by this action. You have x fields. The action on the spanning fields of the orbits act. The action on this spanning vector field is just the adjoint representation. So you have a representation of the orbit which is preserves the metric, and this is somehow the key to try to understand the whole structure of the manifold M. So once you have this kind of result, this kind of theory, from your isometric G action, as I described, preserving the pseudo-Riemannian metric, finite volume with some dense orbits, you get yourself a foliation by G orbits. The orbits are covered G, so you know somehow the structure of the orbits. You also have an action on the tangent bundle to the orbits. Since it preserves the metric, then all action, a representation on the normal bundle to the orbits. You know that the action on the orbits is just the adjoint representation. If for some reason with some conditions, you know that the leaves are non-degenerate, then you can do this decomposition. Somehow you know the behavior of O, it's given by G. To know the whole of your manifold M, the rest is to analyze, to study this normal tangent bundle. And this is going to be encoded in the G modular structure of this normal bundle, which comes from this over here. So that's the basic idea. Take these ingredients and figure out something about your manifold. So I'm going to present some results that provide you structure properties for these pseudo-Riemannian manifolds. The thing is that the behavior is going to be very rigid. Not every manifold cannot. So as before, just to remind you, G is a non-compact simple Lie group, M a finite volume pseudo-Riemannian manifold, and we have an isometric G action on M with some. So what can you say about this? So one important thing is this is a simple group. From the very beginning, we know that this is a pseudo-Riemannian manifold. M itself is a pseudo-Riemannian manifold. So you have two pseudo-Riemannian manifolds that can compare with each other. Both have corresponding indices. Gromov proved that the index of G is less than or equal to the index of the manifold. So the question is whether there is some special behavior in the case of identity. And there is one. With my hypothesis, G a connected isometrically, then solve it. Now I have a compact pseudo-Riemannian manifold. If the indices are the same, then somehow up to a finite cover, you can say precisely what manifold you have. There is a finite cover, some connected Lie group that has G, the group acting as a factor, some lattice, co-compact lattice in the whole group L, and a compact subgroup in the other factor H, so that the action leads to the finite cover, and this finite cover is really the concept. It's really from L, model lattice, and there is this compact stuff acting here. So it has to be basically given by Lie theory. Once you have same index with then so on a compact pseudo-Riemannian manifold, the manifold M has to be given by Lie theory with the constructions I considered before. So as I said, it's very, very rigid. The situation is rigid. There are a number of other results. We can consider two situations, as I mentioned. First, I want to assume that you have this direct sum. For that, using Gromov machinery, you can impose if the dimension of G is less than twice the dimension of M, you always have this. Also, it is possible to see that G orbits carry high invariant metric in G when you. So it's really given by basically by the Killing form. So as I said, there are strong restrictions here just because of the action of G. Now, there are two situations, but I'm going to assume for the rest of this talk that this holds. So somehow it's a low dimension case for M, and two possibilities on the normal bundle, whether it is integrable or not. If the normal bundle is integrable, assuming completeness, you can prove the following result. So somehow similar to the previous one, up to a finite cover, your manifold is a Lie group times your Lie group G acting times some pseudo-Riemannian manifold mod out by some discrete group. So again, some kind of factorization where G has to appear. That's the integrable case. For the non-integrable case of the normal bundle, there are actually more interesting results that you can obtain. Again, I'm going to assume that M is complete and has finite volume. And a number of results in particular cases can be obtained. For example, you have if the action of this special orthogonal group of signature PQ with this, if your manifold, the dimension of the manifold is less than or equal to this number and is given like this, then something similar as before, up to a finite cover, G equivariantly, the manifold is diffeomorphic to the next special orthogonal group mod out by a lattice. So again, just from this action for this particular group, the manifold up to a finite cover has to be given by Lie theory. Another special orthogonal group mod out by a lattice. The other results I have here are kind of similar, the same kind. Take G to be the non-compact real form of type G2 over real numbers, and the dimension is less than or equal to 21, then again, the manifold has to be covered by this special orthogonal group and modeled by lattice. All of these results can be obtained, as I mentioned, using this Gromov Zimmer machinery and the representation on the orthogonal complex. Here is another one. This is interesting because here I no longer have a simple group. I have a product of two simple groups, a semi-simple group. Perfecto. Now, again, with some bound, some conditions, some non-triviality conditions, you can say that your manifold is given by a group. Another result kind of like, because it involves exceptional groups. If your G is one of the non-compact simple Lie groups of type F4 over R, the dimension of M is less than 78, then your manifold is obtained from the exceptional group E6. As you might get, 78 is exactly the dimension of E6. So you have all these kind of results. The situation is very, very rigid. That was the idea in Zimmer's program, and somehow it's being realized with this kind of results in the pseudo-Riemannian situation. Of course, I have a very strong condition here. I'm assuming completeness. What can you say if you do not assume completeness? Without completeness, you can still prove corresponding for all these cases. You have a global realization of your manifold as H mod gamma, but you do have the existence of local isometries to the corresponding quotients. So for example, if you drop in this result the completeness, then you can say that M is locally isometric to the exceptional Lie group E6, and something similar for all other cases. And I guess that's it. Thanks.